Hello and welcome to 18th lecture of the course on corrosion, environmental degradation and surface engineering. This lecture is a second lecture on NDT. It is a non-destructive testing, and then we started this topic testing realizing the importance of testing, because finally our aim is to minimize the failures and minimize the even initiation and progress of the failure, take necessary actions well in advance. So, that is why the testing is important. Now, first slide indicates similar thing. We say that to keep industry running effectively, again we are using the word NDT, is a non-destructive testing is required to inspect complex structures or assemblies. What is the advantage? We do not have to dismantle those systems. So, this is the major importance of the NDT. Without dismantling, without really harming the equipment or stopping the work, we can continuously test the procedure, or we can test continuously the system. And of course, we say that weaknesses and faults in material or in structures can be uncovered, can be discovered, can be figured out using the NDT technique, which is just opposite to the destructive testing. Mostly we use a destructive testing in the beginning itself, when we want to understand the material and we do not have a sufficient data, we do not have a sufficient knowledge, we build on that. Once we have all the knowledge, then understanding of the failures also, then we go ahead with the NDT or the non-destructive testing. And then this is NDT has advantages as mentioned. There was also importance given to the couple of industry. We say aircraft industry really needs to have NDT. Even the pipelines, which are the running kilometers over kilometer, and pipelines are closed also, and if there is a failure, sudden there will be a lot of leakage of the gases or water or maybe the oil. So, we want to avoid all those kind of failures. So, that is why NDT is required. Similarly, pressure vessels. So, these are the very important system and very important for those industries. So, that is why we go ahead with NDT. Of course, we are writing here because we have been giving most of the emphasis on a surface failure. We are not going giving much failure and importance to the complete fracture. In this case, even inside surface something is wrong in a pipeline, I will not be able to understand from outside. So, those failures are also required to detect whether the thickness of the system is, or maybe the component is continuously reducing because of the corrosion, when the failure will occur. So, that is why we are including this also the feature. Even inside surface, if we are able to find out some problems or some crack which is very near to the surface, and maybe after few hundred cycles or few thousand cycles it will come to the surface, can we detect those well in advance? And that is why we see that this is important. Another important thing about NDT is that if we are using established techniques, those techniques are based mostly on standards which have been given by the various societies. So, if we are following some standard practice, standard test, then it will be applicable for everybody, and then we can document, we can publish, we can really share with the industries those documents. And another thing what we see that as we are trying to detect the failure well in advance, so it is economic way. In fact, it makes also to realize that if we have done something wrong, or maybe some cracks have been left, or maybe some manufacturing process is not sufficient to build the equipment or system, those can be detected by NDT, and then we can improve the quality. So, that is why we say that using NDT to find issue leading to the major failure is an economic way to improve the quality control. So, this is a very important for us. And last in this line we say that compared to destructive testing, NDT process is processes are more sustainable. And my earlier lecture we said we mentioned very clearly that there is a sustainable development is required, and to develop sustainable to master sustainability, we require a minimum to minimum rejection. And that is why we say that we should use we should be able to utilize our existing resources in much better manner, and produce minimum waste. That is where the NDT really helps us, is uses a fewer resources and produces a less waste. So, it is really helpful to us. These are the merits of the NDT, that is why we are continuing. However, we have given a lot of importance also to corrosion, and when we discuss NDT or with even the destructive testing, corrosion will be playing a very important role. So, we will be covering few slides on a corrosion or corrosion testing, maybe the destructive testing or non-destructive testing. So, here when think about the corrosion itself, corrosion testing, those testing also can be divided in two groups, that is a destructive testing and non-destructive techniques. So, same division the way we have used for the normal case, the corrosion testing is also a part of that only. Now, in this case what we do the destructive testing, basically we try to measure the weight loss. Is the weight loss positive, is the weight loss negative? Weight loss positive means material has been removed from a surface. Weight loss negative, that means material has been added to this. Now, why the material will get added, we know very well, there are chemical in environments and material will react with that. That means material from environment is getting absorbed on the surface. Actually, the material is coming from outside to the surface, there is a possibility of weight increase. So, that is why we need to count it. Now, we have learned in a wear that there will be always a wear loss, that will be always positive side. However, in corrosion there is a possibility of negative side also, that there is a top surface is swelling, accumulating the material from outside, that is why the weight loss can be negative also. However, this weight loss itself is an indicator of corrosion severity. If the weight loss is significant, naturally we know that severity will be on higher side, or maybe the corrosion process is causing a severe damage to the surface. There is another thing which we have learned, the metallography. Metallographic investigation provides a data to us, and the data can be, and those data will be really useful to predict the life, residual life of the system, and the data will be in the form of the depth of the attack, what is the really penetration of the chemical which is going inside the surface, what is the depth of attack, what is the pitting or maybe the pitting diameter or the pitch diameter, and is there any intragranular corrosion, that means there will be a severe damage where stress level has gone much higher side. So, those things are important, that is why we get those kind of information from metallographic testing. Another we also learned something like a corrosion coupon, and this was covered at least in the two topics of the earlier lecture. What we do in this case particularly, we make a number of coupon, maybe 100, 200, 500, and we want to test really how corrosion is progressing. Is it a linear progression, is it a non-linear progression, and basically we can give a percentage of chemical or increase a percentage of chemical and figure out what is the really corrosion rate on that. That means, if the H2SO4 or maybe say sulfuric acid is used against some component, if I am increasing the percentage, what will be happening to the material? Will there be any minimum limit, will there be any upper limit, something like that we can figure out using the corrosion coupons, because we expose material in similar conditions. So, that is why we say the coupons which we use particularly for this kind of destructive testing need to be made from materials which have the material of the system, same material will be utilized for this purpose. Another thing which came into the mind is something like a mechanical testing. What will happen if the corrosion is happening, and I give an example of like an intragranular corrosion or maybe pitting, something like that. So, there are cracks or maybe deep cracks possible. Will there be any damage to the material strength? Will it be tensile strength will come down, compressive strength will be lesser, bending strength will be lesser. Those things can be figured out using the mechanical testing, particularly when the material is subjected to corrosion. So, material testing after corrosion. Keeping the non-destructive testing is the same, we go with visual observation or visual inspection, ultrasonic testing. These two topics have already been covered in our previous lecture, and then we will be taking few examples particularly pertaining to the corrosion. So, what will happen in the corrosion case of visual inspection, what kind of UT can be done in the corrosion testing. We will be also covering the radiographic testing in the present lecture. Remaining methods will be covered in the next topic, that is NDT 3. Now, if I want to express in this in other words, what will be that? We can really express our weight loss. Something we say that in weight loss testing, weight is measured before and after the test. The same thing what we do in a wear testing, and the difference in the weight value suggests the severity of corrosion. If weight loss is very high, then actually severity will be very high. If weight loss is negligible, 0, then we will say there is no severity of corrosion. And if it is turning out to be negative, then we say the material is getting accumulated from outside. Now, here there is one problem also, like if volume is continuously increasing or mass is continuously increasing, but there is a possibility of the thermal crack, or maybe say the additional cracking happening in the material. So, we will be covering one of the example where the weight overall will increase or weight loss will be negative, and then dimension of the material will increase, and it will cause some sort of damage to the concrete, particularly the reinforcement. The material which gets corroded inside, and there is no removal, continuously accumulation. The diameter may be 13 mm initially, becomes a 15 mm, 16 mm or 30 mm. Naturally, the material is getting added, and then there is the overall structure, and there is a unbalance in this situation. Naturally, there will be generation of more and more generation, more and more expansion of the cracks will happen, and finally, the whole system will break. So, even though material loss is a negative side, again it is of the concern what will happen to the dimension. So, that is very important for us to understand. So, from that point of view, weight loss testing is a very important. And metallography, which we already have covered, but in this case again we need to really look at the cross section of corroded material. We need to prepare it, as I mentioned earlier. In destructive testing, we mostly make the samples. So, samples are prepared. In this case, we need to etch and then examine under the microscope. It can be any microscope, it can be optical, it can be SEM, it can be TEM, depends on what is really requirement. So, this kind of a technique will reveal the corrosion damage, and corrosion damage may be something like what is the extent of attack, pitting and intergranular corrosion, which I expressed earlier also. Now, as I mentioned, the testing coupon, obviously the testing corrosion coupon, we make many coupons, so that we can evaluate or we can follow some sort of trend or do a trend analysis. So, we can say the testing corrosion coupon is a standard technique for evaluating and monitoring corrosion rates in industrial system. Coupons are typically rectangular shape. I covered earlier this kind of a shape showed in one of the earlier lecture, but mostly they are rectangular in shape, but sometime it can be also circular cross section also, or we say that the other shapes are also possible. Most typically is a rectangular, maybe than circular. So, the coupons are typically rectangular in shape and made of the same material which I already expressed as the system component and exposed to the similar environment. Main thing is that we need to simulate similar kind of environment. It can be scaled down, it can be scaled up, depends on the material, whether we are going from micro to micro or nano to micro to understand the complete system. So, this is what we really require, and then what we do, periodically removing and analyzing the coupons. So, if there are 100 coupons and we want to do what happens over the 100 days. So, I can remove one coupon every day. So, first coupon maybe has been exposed for only 1 day, second coupon for the 2 days, third coupon for 3rd days, is something like that. So, we can say that by periodically removing and analyzing these coupons, we can access the corrosion rate, determine the type of the corrosion which occur. Quite possible the corrosion modes may change also. Initially there is only one mode, but after 5 days, after 10 days or 15 days, additional other corrosion has happened, and it is accumulating, or maybe said it is enhancing significantly. So, we can really figure out what is the root cause failure and what is really the important factor, what is the main factor which is enhancing the corrosion drastically. So, those things are possible when we go ahead with the testing corrosion coupon, and then this is very important for us. In the future also we can think and keep a good control. We say that we have learned each and everything, and now we want to test in a very maybe say that we want to make a system under control. So, we can really play with the control system on that. So, we can say the effect of the corrosion induced degradation in terms of the tensile, bending, even the impact testing can be determined using this kind of process or using this kind of testing. So, it is really helping, is really giving a lot of data to us, so that a more and more understanding maybe occurs. Like I can test in maybe some acidic environment or some sort of a NCl maybe the sodium chloride environment. I can figure out what is happening of with the sodium chloride over the period, or maybe what is happening when the exposure is towards the kind of HCl, or maybe say nitric acid, or maybe sulfuric acid, something like that. Now, while we say the non-destructive visual testing, which I have already covered in earlier lecture, and corrosion will give some sort of a discoloration, particularly when we are talking about the corrosion. It can really discolor the system or with the component, it can really give a number of pits on the surface. We can understand from that point of view. And then ultrasonic testing is very important to figure out which we are not able to find on the surface. Maybe the failure is not happening on the surface, there is a subsurface, and then maybe say as a crevice kind of corrosion, inside there is a more damage compared to on the surface. So, in that situation naturally we will not go for the visual observation, we go for kind of the UT test or maybe some other test, what will be radiography, which will be we will be covering in this topic lecture, that also can be utilized for this. Now, we have also covered in the UT that there is a transmission and reflection also. So, then we can really figure out what is the right method for us to utilize it and get that kind of signal, and then give a prediction based on that. So, this is now I am just trying to cover one of the research paper which was published in 2018. This is 2018 in this case, and what they try to realize the corrosion behavior of aluminum 7075 and under the different kind of mixing. So, what they did, they mix silicon carbide 1%, 2%, 3% and 4%, and different kind of environment, something like HCl, sulfuric acid, and NaCl, that is a salt solution in this situation. And then if you look at then of course they expose the samples, whatever they say, they made the samples expose for the 96 hours they dip the in solution those samples for the 96 hours, and after that they started measuring the weight loss. What is the really weight loss, and then based on that they try to figure out what will be the corrosion rate, and the corrosion rate mm per year has been given in this form. And you can see here that there is a red color is sulfuric acid in all 4 figures. So, 1, 2, 3, 4, in all 4 figures that the sulfuric acid is causing more and more damage compared to the HCl. HCl comes at number 2. And the what is the NaCl, the salt solution, is not really affecting at all in this case. So, what has been this? This is for the pure aluminum alloy. This is aluminum alloy with the 2% nanosilicon carbide. This is an aluminum alloy with a 4% nanosilicon carbide, and they are mixing, making a hybrid composition. That is a 4% silicon carbide and then 4% aluminum oxide also. So, they are using some sort of a hybrid combination and then trying to figure out what will be the rate of the corrosion, whether this kind of a new material which is invented and one of the top research area in recent time, that if you do more and more material research, well, that there will be a control on a corrosion rate. Yeah, and they found it, yes. And corrosion rate in this case they predicted maybe say in pure alloy, you can see the corrosion rate in the 2 is reduced. Here the maximum value is a 0.14, while in this case the maximum value is a 0.08 something. Now, coming to the third case, they do not find that has again increased to the 0.12. That means when they are using 2% nanosilicon carbide, it is working fine, but when you increase it to the 4%, maybe number of cracks has increased, or maybe the discontinuity has increased, maybe the and then the homogeneity has decreased in this situation. And then finally, when they are compensating that 4% addition, whatever the drawback has come, they are trying to bridge that with aluminum oxide, and they find that there is a really some sort of improvement in the reduction in a corrosion rate or improvement in a overall kind of performance. The mass loss is not really going on the higher side. So, this kind of research indicates us that if we go for better and better material, and if we have a techniques because we can do a lot of innovation, but unless there is a validity, we can brainstorm a lot, but unless there is a validity on that, yes, whatever we are doing, it is really moving in the right direction, we cannot really innovate, we cannot really make a good products. So, in this case what they try to they reutilize, or maybe they utilize and the knowledge of nanoparticles, and then they say that if we add nanoparticles, and then it will give a better and better results. However, except this 4% silicon carbide, we find that the 2% silicon carbide is giving a better results compared to the 4%. However, if we add 4% alumina, making a hybrid combination, that gives a far better results compared to the any of these three. So, this is the best. So, this is giving the best results to us, and it has been concluded based on what we have tested. If we do not test, we will not be able to conclude, and this is the reference is being given in 2018, it was published in 2018. Now, coming to the metallography, and again I am trying to cover from literature, the 2019 there is a paper on the metallography and corrosion of ancient Chinese bimetallic bronze sword. Earlier we know that the swords were made of the bronze material, and then they excavated, and then they found that this kind of a sword was somewhat available in some period, something like a 476 the 476 to 221 BC, long time back, and it has been excavated from China, and then they find that this is the lower portion, and then which can be used in a hand to then hold it, and this is the extended portion and the length, and then they find this is the same portion, this portion and this portion is same, and then they find that the sword is broken, and then there is a lot of degradation of the material, there is a lot of degradation, the removal of the material also has happened. And one of the major important thing is that earlier there was some case study, and then they say that this kind of sword generally contain 23% tin, and then this case study they find the 16% tin. That means if the earlier study was correct, that means there is a possibility, there are two possibilities. One is that there is a corrosion and material is getting removed, or tin has been getting transferred from that section to some other section. Another possibility is that there is a lot of variability, some section will give 23% tin, some section will give a 16% tin. So, it means there was some sort of drawbacks in a casting method, there was some drawbacks in manufacturing method, and then by that time they were not knowing how to make a homogeneous mixture, or how to homogenize the overall composition of the sword. So, that is what they express. And then they use optical micrograph, and then the optical microscope, and they use also the XRD, the X-ray diffraction pattern, to analyze the microstructure and corrosion phases of the bimetallic sword, and then they have present the results based on that. Now, they observe the corrosion. This sword is not in an intact position, it has been broken, it has been corroded. Question comes, why? Naturally, they try to conclude that corrosion phenomena has occurred because of the burial environment. So, even in the sand there is some sort of corrosive environment from which it has come. They say that there is a possibility of decomposition of the bones. So, there were some bones, and the bones get decomposed, and then the bones provide insoluble pyromorphite that acts as a kind of a chemical, and it makes it helps to make a chemical cell and around the sword, and naturally there will be degradation. So, this kind of study really helps to understand. Now, if anything ancient which we have, we want to preserve it for the years and years, what kind of environment is really required. So, this test really helps. And then another thing what they mentioned, that there were some sort of void and the cracks which are really providing the active environment in presence of the solution, which is a corrosive in producing corrosive environment. In addition, there are voids, there are cracks which are allowing helping to make a kind of electrochemical cell. So, the more and more corrosion happens, and more migration and redeposition of metal happens. This is what I mentioned, that tin may be have removed from or migrated from one section, and it has gone moved to the redeposited to other section. That is why there is a separate different kind of chemical composition is really coming at a different section. Now, to make a stable environment for the, or maybe to preserve this kind of antique thing, what is really required, we say that the sword can be stable if we remove all active corrosion medias. So, corrosive media need to be removed, as well as kind of the portions which are maybe the like a cracks or the voids, if can be filled and can be removed, that will give a good result. So, many times if there is a crack, if you fill with some sort of material, it will stop and maybe at least it delay the corrosion procedure. We will cover one of the case studies in present lecture that will indicate how the corrosion process can be delayed by bridging those cracks, by filling those cracks also. So, in this case, we sword will be stable without active, if we are removing the active corrosion, and it will be appropriate to store bimetallic sword or maybe similar kind of a material or maybe similar kind of artifact in a dry and clean environment to preserve any antique artifact or sword in this case. So, this is a case study. Now, they also provided a details, and then what they are shown that they provide one table indicating that there is a difference in phases also. We know there are alpha phase, beta phase, delta phase, epsilon is generally we do not find in this kind of steel or maybe the bronze epsilon, but it a very small section, something like epsilon comes around 0.5% has been observed in this kind of sword, and then they find that two different type of alpha phases, not only one alpha phase, but there are two different type of alpha phase, one contain 14% tin, other contain 10.2% tin. So, there are two different alpha phases available present in this kind of sword. Of course, they did a XRD and then they figure out and then they try to spot there are some sort of green patches and the yellow patches, and that means there is indicating the different kind of phases of the corrosions are there. And in this case also they find the green color, red color and yellow is already there. In addition, there are some sort of other corrosive products available on the surface also. So, these are the important, and then they could conclude that there is a non-uniform distribution of elements within alloy. There may some sort of chemical action happening, and then there is a more and more non-uniformity is getting we say coming into the picture. And then if that is not happening in a current time, that means when they did really manufacturing, maybe there was some sort of non-uniformity and which has come from a cooling and solidification process. That means whatever the manufacturing process was opted that time even that there was a non-uniformity, there was no uniform cooling, there was no uniform solidification. That is why there is a migration of the material, and somewhere we are getting one kind of chemical composition, some other portion we are getting another chemical composition. So, it may happen over the period because of burial environment, because of chemical reaction, or maybe that the manufacturing time itself those things were not the uniform, and they were not able to keep it uniform. So, both options are possible in this situation. Now, that is another third what we say the corrosion coupon testing, and as I mentioned we generally go with many coupons, it is not one or two coupons. So, in this case we are trying to take an example of elemental sulfur and what will be impact on mild steel. So, we say the impact of elemental sulfur on corrosion of mild steel, and this is the mild steel in this case. This is elemental what do we say the sulfur has been capped. Now, if you keep this unit for almost for the 4 days, even at the room temperature, and they found that a lot of iron oxide sulfide gets on the surface, and instead of this kind of the surface and this kind of color, everything becomes a black on the top, and that is because of the iron sulfide. So, that means if an elemental surface is exposed to the mild steel, naturally it will corrode the mild steel and it will make iron sulfide, which is a black color, and if you leave for the more and more number of days, then the layer will be thicker and thicker. That is why we say that elemental sulfur can cause a localized corrosion process. I am using the word localized, reason being if there is a presence of water, then it will be generalized corrosion, it will be aqueous corrosion. But if there is no water, then it will cause some sort of a localized corrosion and the surface of the mild steel, and which will come whenever the elemental sulfur will come in a close contact with a metal or a steel, then it will corrode the surface. And this has been shown. However, as I mentioned that we are using the word localized corrosion, but if there is a water available, then what will happen, hydrolysis of this elemental sulfur will occur, and it will have some sort of a sulfuric acid will be formed, and that will give a lot of was a corrosion at the temperature, particularly the process happen particularly the temperature is more than 80 degree. So, then the whole solution which is available, it will cause the severe wear and the severe corrosion, while in this case is a localized corrosion. So, this is a localized corrosion, but if you go ahead with and the water or hydrolysis of the elemental sulfur, then there will be acid formation, and that will increase acidity of the solution. Here is a localized, and in the other case it will be a generalized one. So, when you try to test it, what will happen, we require a temperature. This was done at the 25 degree, and with what we are talking about 80 degree. So, localized at the lower temperature, while formation of the solution or acidic solution at the high temperature. So, we need to really figure out what is really happening with the temperature, what is really happening with the time, because here we are talking about the 4 days. Naturally, it has been observed for the 4 days. We can't keep it for the 4 days, and we need to really look at what happened after 1 day, what happened after 2 days, what happened after 3rd day, or if we want a much more refinement, what happened every 12 hours or something like that. So, what we really required, effect of the temperature on acidification of water, particularly when it is the elemental sulfur is exposed to the water, or maybe the use in that case. So, it is really required a series of experiments, series of studies, it is not a one. So, there the corrosion coupon testing will turn out to be very useful, because we are going to use many coupons, it is not only one. And again we are going to make the material, use a similar material, we will make a coupon from the same material, and then we will give a different kind of exposure time and temperature, and we can figure out what is really happening, and we can compile the good results. While in this kind of test, and this study has been done by Fang et al. And the publication is in 2008. So, they kept the temperature range between 25 degree centigrade to 150 degree centigrade. So, results have been presented in that kind of this reference which has been listed over here. Now, if I just summarize the final results of their work, we say that the one good thing about this coupon is that whatever the required data or images which we really require, directly can come from a corrosion coupons, and then as I may say with the time also. So, this is one of the corrosion coupon, and then you can see here this sample is around 2 mm, maybe the corrosion side is as such, or maybe the dimension is around 10 mm in this case. While if you look at it, they are trying to show this one small patch, and this patch has been shown after magnification at the 100 micron scale from 2 mm to 100 micron, and then we are able to find out some sort of a curved edge on this. And now further, if we amplify it, magnify it, then at the 10 micron level we are able to see number of lines on the surface also, right, and that has been mentioned here. After 4 days at a 25 degree centigrade, whatever they observe, a denser film forms on the surface. So, this is the one of the denser film, or maybe the thicker film. It is not a mild steel, it is a kind of sulphide on the surface, and then it has been mentioned over here. Then moreover, exfoliation is coming, the layer is coming its own, is we are not doing really any removal from removal of material as such. It is coming on that the exfoliation of the film is visible, as we go ahead with a magnification like 2 mm, even we are able to see that visible, and then this coupon has a more severe cracking than exposed to 1 day. That means they compare, this is after 4 days, but they compare with the 1 day, and then the exposure after 1 day, what will happen, or maybe the material coupon which is coming, or maybe the surface which has been shown after 1 day. Actually, if compared to 1 day, this is a much more severe damage. So, that there is no passivation within a 1 day itself. Many times we say the passive corrosion after 1 day stop, no further change. So, then in the situation, what would have been the results? After 1 day, after 4 days, there is no significant change. that means the layer is same, but then the changes are not happening, while they indicated this coupon has a more severe film cracking than which when it was exposed for 1 day. So, that means there is a progression in a corrosion. And another thing what we are able to observe in this case, these kind of lines, you say the polishing traces on the original steel substrate, because the coating is happening or this layer getting deposited or iron sulphide is formed on the surface. So, that we need to look at what was the initial original surface, a steel substrate, and if there were some sort of marks or maybe the polishing traces, those have also getting a transfer to sulphide film. So, that is what is a polishing traces on original steel substrate left an imprint on the sulphide film formed by the solid state chemical reaction. So, there was a solid state chemical reaction, iron sulphur on the iron and the sulphur form the iron sulphide, and if you allow more and more days, it will become a thicker and thicker, and it is because of solid reaction, whatever the surface roughness of the mild steel, it is also coming directly on a iron sulphide. So, this is what then the solid because of the very intimacy between the two surfaces, this is getting transferred, the surface texture is getting transferred on the other film. Now, that is what we has been shown over here. Again this has been the same paper which we have referred in previous slide, the same paper has been referred in this case. Now, there is another the point which we discussed, something there is a possibility of the damage of the material property or maybe the lesser tensile strength, lesser bending strength. So, that to understand that and then we require mechanical testing, and that is why this heading says corrosion testing, mechanical testing as such. To understand that kind of effect, what we really require, we require samples, the way we have mentioned in the earlier corrosion coupon testing. So, we really require that kind of thing, and then there is a one case study available in the literature which was published in 2019, we have picked up that we say that corrosion effect on a sintered 316L stainless steel. Now, here Al means low carbon, that is what we shown, suffix Al indicates a low carbon content, and carbon content is kind of a 0.02, and most of the stainless steel material the carbon content is on higher side, maybe something like a 0.06, 0.08 something like that. However, we in this case it has been kept purposefully low, but you can see this is a stainless steel, chromium percent is 17%, nickel percent is 12.75%, and molybdenum also is 2.15%. So, these are the stainless steel materials. Now, naturally question comes how do we go ahead and then how do we do a material testing, particularly corrosion testing. So, they use a kind of a salt fog or salt spray test, and then they made a chamber, and then they did a cyclic exposure of corrosive media on a steel surface, samples which was made from a sintered 316Al stainless steel, and chemical composition has been given over here. Now, they use the SLMS equipment. What is SLM? Is a selective laser melting. We can take a powder, maybe say roughly 100 micron size particle with spherical shape, and then we can melt, and then we can really give a now we can prepare the sample. This is what the recently additive manufacturing has come. And so, in this case it has been shown that this is a LT is a layer thickness which we can control. They kept a layer thickness, each case maybe around 30 micron. They made a sample, and then there is a layer, and then we are melting it, it will form a thick layer. It can be thicker also, depends on how many passes we want to use. They kept something like a different environment, particularly nitrogen environment, so the other activities can be stopped completely, only the melting of the material happens, and then we are able to get a good sample without any exposure to oxidized environment. And then this is what they have done, and then finally they presented results on this. They made also that for the material testing, they made this dog bone specimen shape as per the standard ASTM E8 AM standards has been given. This is a standard has been shown over here, Of course, they use a 3 process or 3 different kind of manufacturing processes. One is the sample 1, the one manufacturing process, sample 1, second manufacturing sample 2, and third manufacturing sample 3 they have used. Now, what is this difference in a manufacturing process when we are using the additive manufacturing process, or we say we are using only the SLM manufacturing process, but now they have a change the power rating, power setting of this. So, the first case the power rating and the setting is minimum, and the third case power setting is a maximum. While coming to the first case S1, this velocity has been capped to 200 mm per second, while in this S2 the velocity has increased to 300, while in third case it has again dropped back. So, however, the energy level which has been given to the material is a maximum in the last case, the third case, while number 2 S2 is a roughly 188.9, which is very close to 188.3 as it was given to the surface S1 manufacturing process. They showed in the microstructure of the sample also. You can see here in A, this represents S1, B represents S2, and C represents S3. We are able to see some sort of a corrosion mark, maybe irregular shape and corrosion mark in sample 1, whilst 2 and 3 look like more or less same, while and then we do not have much corrosion mark. However, milling marks or whatever the sample polishing mark are available in all 3. So, in S1 also we are able to see polishing mark, S2 also we are able to see polishing mark, S3 also we are able to see polishing mark. Now, this is what I was mentioning about the mass loss kind of a bar chart, and then it has been shown over here. So, this is the mass loss of a specimen and the function of exposure of time. So, exposure is 0 hour, 24 hours, and last one is a 240 hours. So, what is it really and this is basically a simple salt. It is not very chemically reactive surface, but still the corrosion is happening in this case. So, in a 0 hour the starting we do not have to think much about. Coming to the second one, we find significant loss of the material than the sample 2. The sample 2, there is a significant loss of this sample, even though surface texture is good, surface roughness is good, surface appearance is good, but it is causing a huge mass loss. If you look at the red color, this is the red color patch is very small, significant and significantly much lesser than the S2. S1 we are able to see some sort of corrosion, some sort of uneven surface, but still the mass loss is lesser. So, we need to understand why. Now, coming to the after 96 hour, we find a very little accumulation in maybe material loss at the samples S3, at the group of S3, while the reduction has happened from around 50 milligram per centimeter square to roughly 10 milligrams. So, almost the reduction has happened, it is not really. So, there is some sort of passivation is happening, and then it is not as reactive earlier. After 24 hours whatever we got, after 96 hours we are getting only 20%. So, significant reduction in the chemical activity has happened. While coming to the S1, S1 has accumulated the material on the surface. So, that is why the weight loss is a negative side. So, in fact, this material, this sample S1 is really accumulating the material. Now, after 186 hours, again in the accumulation in the case of the S2 has gone very high. So, in this case material loss is not happening, in fact material gain is happening. So, these are the process, and the after 240 hours again we find the S2 is very sensitive compared to the S1, but however S3 remains very good, not losing material, not gaining material, that means it is turning out to be more like chemical inactive. Again there is the material is same, 316L. Testing specimen, geometry, everything is same, only what has changed has been changed only the energy level which is exposed to the surface. So, manufacturing process is only fine tuned. Now, material same, but material manufacturing process is fine tuned, and we find significant difference in the results. So, this is where we say that when we go for the testing and we figure out and we can really tune, we can make really then the manufacturing process perfect for the particular situation, particular condition. If I want to express in my word, we can say S1 sample, which we saw in a figure. S1 sample exhibit irregular and non-uniform surface, where S2 and S3 sample exhibited uniform surface without visible cracks. While in S1 we could see the samples were kind of having some sort of crack or defect and some sort of corrosions also. So, another thing is that we are able to see some sort of marks. It can be the milling marks, it can be surface grinding marks, depends, because we have seen on a magnified view. And then when experiments were done, those were done in a salt spray experiment, the kind of the fog environment or vapor environment, and then to evaluate what will be the corrosion behavior of this material. And we could figure out there is a weight variation. So, variation in the weight of the 3 samples group throughout the exfoliation test, corrosion test were shown, particularly shown in the figure. This variation in the weight represent the both, as I say, the mass gain as well as the mass loss. Generally in a wear test we look at only the wear loss, while in this case we are looking at the both. That is why the corrosion test is slightly different than the wear test. What we found that S1 group of the sample exhibited a low mass loss during the first 24 hours, followed by the variable weight gain, as we seen the negative the weight loss was a negative. So, it was basically the gain. So, variable weight gain as the exposure duration increase. In contrast, S2 sample group encountered significant mass during initial 96 hours. And in this case, and after the initial period, there was again mass gain. That means initially they were losing material, and after that they started gaining the material, this kind of samples. And then even the significant difference between two, there is only very slight variation in energy level. One was a 188.3, other one was a 188.9. So, even the slight variation in energy, but causing a huge variation in the properties. However, what we can conclude from that, the S3 sample group exhibited a less corrosion than S1 and S2 groups, and then their behavior can be the main attribution is that they have kept a very good surface, and moreover kind of a chemical inactivity compared to the other two materials. So, chemical inactivity has been formed or made because of the manufacturing process. Now, they also have given a microstructure, as I say, the metallography. So, they have given a microstructure. You can see here there are many cracks and irregularities in the case of the S1. Similarly, we are able to find some sort of irregularities in S2 also, while S3 is more or less good. However, we are able to find some sort of irregularities after 96 hours. That is why we looking at the bars of the different sample, we found there is some sort of weight loss after 96 hours, and that is indicative over here. While in this case 96 hours we are able to find out the deep crack in this, or maybe the pit formation, and this is continuously increasing. Then this pit is continuously increasing, and then up to 240 hours this also has gone very high. And in that way, that after 240 hours it has come to the visible sign, something like that. So, this is each what we were talking about, the 20 micron something, this is a 20 micron. Now, here we are looking at the 1 mm, it is not a 200 micron, we are looking at the 1 mm, and that is visible on the edge of the surface. So, overall even though weight loss, the loss and gain is not that very high case of the S1, but the microstructure revealed that there is a severe problems in a surface. Well, coming to the S2, significant defects have been visible in after 24 hours, but this defect have come down, but we are able to see still the crevices, we are able to see some sort of the micro pits formation in the S2 also. While in S3 in the only after 24 hours of operation we are able to see the significant variation, while after 186 hours, sorry, at the 96 we are able to find more variation, while 168, 240 not much. So, what we can say, surface morphology of the specimen from each group has been shown, and this is basically exposure to the salt. The results have been shown for 24 hours, 96 hours, 168 hours, 240 hours, and then we are able to see the pits we are able to the crevices, see the crevices also, these are all the crevices are available over here, and then we are able to see the cracks also, the cracks are also been visible. These are the, we can say these are the these are the common form of corrosion, and the two in a stainless steel surfaces in a steel material. So, this kind of corrosion will occur. If I want to express in my words, I will say that when conducting corrosion test, it is essential to evaluate the surface profile better, or maybe say the instead of surface profile we say metallography. So, that will give better and better understanding. We could see that the surface of the S1 group developed a random kind of a round kind of the pits, dimensions are also different, and then depth, which we could not measure in this case, but the depth is also different. As the duration of exposure increase, the fissure has become maybe the cracks have become more pronounced and grow in a size. Eventually, after 240 hours concentrated corrosion, particularly even the 1 mm length, it became visible. Initially it was, we were looking at only SEM images, but finally after 240 hours it became visible on the edge of the sample as such, and then image has been shown to you that the 1 mm it is visible as such. Now, coming to the SEM micrograph on the surface of S3, there is a substantial less severe, of course I am saying still there is a wear, but substantially lesser wear compared to S2 and S1. In addition, the S3 exhibited some sort of localized corrosion or some sort of pit after 96 hours. The reason being maybe there is some sort of a defect in matrix, and if we further improve the manufacturing process, that also can be minimized. So, if I want to say that the S1 group, even though mass loss and all, it has not been substantial, and S2 has much more sensitive for that, but while coming to the metrography, we say no, S2 compared to S2, S1 is the worse side and S3 is the best among 3. However, even S3 we found after 96 hours there is some sort of weakness in the matrix, and that required more refinement in a manufacturing process. Now, finally, they have this was the main test. The main aim of the test was to figure out what has happened or what is happening to the material property. So, that is why they have given this kind of a diagram. It is a tensile test on a specimen, and they have given a results of elongation, they have given results of yield strength, and they have given results of UTS, also or ultimate tensile strength. So, this case this is for sample 1, we are able to see there is a significant difference in S1 and S2. So, yield strength is substantially lower for the S1 compared to S2, and then there is no significant change in S1 and S2 and S3 yield strength, but in the elongation is still there. That means this kind will cause a ductile failure, while this will cause a completely brittle failure. And the last one, ultimate tensile strength, is the highest for the S3. Now, if we compare, we will say that comparison between S1 and S2. In this case, energy level was more or less same, 188.3 and 188.9, while in the case this laser and scanning and velocity was increased, because when you move from S1 to S2, they increase the velocity, scanning velocity, and the laser also power. While in this another thing, this has been shown that ultimate tensile strength increases by 297 megapascal, while yield strength increased by the 268 megapascal. So, there is a substantial change, even the same chemical composition, same thing, but kind of the manufacturing process changes a lot, almost 297 and 269 megapascal change in ultimate tensile strength and yield strength. Now, comparing to S2 and S3, of course, there is a substantial change in energy level which has been utilized for the S3, and then in this case particularly the scanning velocity was reduced. They find a substantial increase in ultimate tensile strength and strength, what do we say, the elongation, while no significant change in the yield strength. So, this kind of understand that this kind of data really will provide some sort of more creativity how to improve each and everything. Now, ultimate tenderness and strength has increased, but yield strength has not increased substantially. So, naturally we need to work on the really matrix side, what is really what kind of further improvement are possible utilizing this. So, what we can conclude from this is a sample deposited the maximum energy exhibited the less corrosion due to the low defect distribution. When high energy is being given, chances of localized deformation or distribution reduces. There will be more and more uniformity in distribution. That is what they will say that due to low defect distribution within a sample. So, more and more uniformity as the corrosion process progress. They did not find any problem with the material properties, even though after maybe say number of hours they find the material properties are not changing significantly. That does not mean that will be always for everything. This was only exposure to the NaCl, that is a salt or weak salt. It is not a very strong chemical or not acid formation. However, if anything goes, in this case they try to demonstrate the process, and after that they concluded that even exposure maybe say over the 200 hour plus, there is no substantial change in the material properties. However, during manufacturing process itself there is a substantial change, but exposure of the corrosive media is not causing a substantial change. So, these points need to be considered appropriately, and we need to account, and again we are not concluding that every corrosion reaction will give a similar kind of effect. NaCl may not give a substantial change, but quite possible sulfuric acid, HCl, nitric acid, they give one of the significant change. So, every new chemical, new composition, new material need to be tested and then figure out what kind of mechanism will be there. There is no uniform rule, there is no uniform policy, or maybe say mechanism which can explain each and everything. So, that is why we really require testing for each and every case. Now, we are coming to the NDT particularly for corrosion, and then we say the first one is a visual testing, which we covered earlier in a previous lecture, and in the same thing has been done was done, and we had taken a reference in 2015, and what has been they have improved the testing method. We say instead of visual testing they have given a name something like a texture digital analysis. So, texture digital analysis is kind of improvement in a visual testing. They were trying to do automation instead of looking with the naked eyes, or maybe some magnified using the magnified device. Can we do automation and then figure out what is really happening? So, that has been given in this paper, and then they have given the results also. Zero corrosion after day 2 they found some sort of corrosion, and as you can see here the more and more corrosion is happening, and then finally this is a severe corrosion they have concluded. So, this is basically automated the visual examination, and then they mention everything on a texture analysis. Based on the top surface texture, we can really predict what is happening with the corrosion, what is happening with the material, what kind of the level of corrosion. Is it a mild corrosion, is it a medium corrosion, is it severe corrosion, or noser corrosion. So, that is why they say the zero corrosion, severe corrosion. So, more and more testing will allow us to understand more, and this has been shown the day 44 the corrosion is severe level. Of course, this kind of data really help to find out what will be the residual life, and some crack has been initiated, some corrosion is there, and then we can really predict what will be the overall life of that system. So, this kind of experiments, so this kind of testing are important. So, in this case what we say automated visual examination on a basis of a texture analysis, and then they documented images up to 45 days. Of course, they have shown only the 10 images, not all the images have been shown. We will have a 44 plus images, and then they mention about the corrosion of steel, that is ASTM AS36 standard, and of course, they wanted to figure out what will be the change in the features. Is basically kind of capturing image, diagnosing image, and then predicting what will be happening to that. So, this is basically kind of the initial tool for the machine learning. We observe and then we make an algorithm so that in future everything can be automated. That is why they use the word automated visual examination. Now, this is what we are saying. This is basically, in this case, camera itself is acting as tool or acting as a sensor, and if we have a mechanism known, if we know that what is really happening, we can write algorithm. The overall testing procedure can be simplified. That is why they say it is a low cost, low tech alternative to the costly testing method. So, if I go, instead of going for the costly equipment, radiography is one of the very costly testing method. So, compared to that, if you take a camera, if you have an understanding about the mechanics of the failure, or then we can make a complete algorithm, we can detect well in advance what is really going to happen. So, this is what in this case they use only camera and processor with a few algorithm and then develop a kind of a testing method. So, this process is important to understand. Overall it really helps to the material scientist, to the metallurgist, and to the mechanical engineer to predict well in advance by understanding this kind of a phenomena. And then if we are able to analyze the texture, surface texture, then the visual testing is also really very helpful, which is a cost economic, less costlier, or maybe say that even the low tech also. We do not really require a training, because even whatever the testing you do, even the radiography technology is little in depth, we need to understand, and then it takes time, it really requires skills to operate that. Now, another test which we have covered earlier, one is something like ultrasonic testing. And ultrasonic testing, something like in this case the same thing has been shown here. As I already mentioned, there is a concrete, and this concrete itself is a reinforced concrete. Basically it has some sort of a steel bar, and a steel bar can get an exposure of the corrosive media, is something like a chloride solution. And then if the chloride really ingrates to the steel surface, then what will happen, that there will be corrosion of the surface. And if there is a corrosion of the surface, quite possible the dimension, as I mentioned here, D3, then the 13 mm can grow to D15, can grow to D20, and there will be a kind of expansion of the surface, and concrete will start developing a lot of tensile stress. And we know the concrete is not very good in tensile, it is very good in compression, but not in a good tensile loading. And then the cracks will form, and under more cracks, more and more chances of the corrosion will occur. We know that cracks will be kind of initiation for they act as a kind of source of the corrosion itself. They give a path to the electrochemical solution. They allow to form a chemical cell or electrochemical cell, and then increase the corrosion rate. So, that is what has been shown over here. And then we are showing here the two sensors to detect the kind of to send ultrasonic waves, and maybe collect those ultrasonic waves back, and then predict what is really happening. Is there any crack, subsurface crack? See, on the surface we do not really require sophisticated equipment, but subsurface we really require sophisticated equipment, because we know today a subsurface crack is there. It will lead to the surface, maybe say after a few hundred cycles or maybe a few thousand cycles, and then that kind of failure will be kind of catastrophic failure, damages will be more, and then we want to predict everything well in advance. So, in this case we say the corrosion of the steel reinforced bar, that is now the new word comes is a rebar. That is a steel reinforced bar, shorten the useful life of concrete buildings. And if the most of the time we say the concrete building is up to the 50 years, but if there is a corrosion, maybe there is a drainage water, and there is some sort of chemical and it is passed to the concrete, naturally there will be some sort of shortening of the life, and that is what we say, the shortening useful life of the concrete building. Corrosion of the rebar and development of corrosion induced cracks. This is what we say in case of the normal and accelerated test can be evaluated if there is some sort of course, when we want to do a testing, we can really develop a crack from our side, and then develop algorithm based on that, and then we can go to the unknown kind of a concrete, where we try to predict based on whatever we have extracted the feature from our earlier knowledge. So, we say when corrosion is present, what will happen to the ultrasonic wave, which we are seeing, amplitude of the recorded wave will be reduced compared to when it is a no corrosion. So, corrosion and no corrosion, in both the cases if we send ultrasonic waves, in case of the corrosion the recorded waves amplitude will be lesser, there will be more like an scattering of the wave and collection will be lesser. It is not directional because there are already cracks, so directionality will reduce, diffraction will increase and energy which we are going to get or amplitude we are going to get, it will reduce. So, this is a way the algorithm can be written after understanding, after really doing the testing on that. We say the ultrasonic wave attenuation due to corrosion induced cracking can be detected by analyzing the energy spectrum. So, if we collect and we analyze the energy spectrum or maybe the only amplitude itself, we find there is a change. Now, this case study has been picked up from a 2014 literature or maybe the research paper, and then they use concrete chemical composition has been shown over here. Now, this ratio has been shown 50%, that is what we say water to cement ratio is 50%. And of course, we know that every concrete need to be kept for some time, so that it get cured. So, they cure it for the 28 days, the 28 the damp curing period was used. So, that now they get sufficient strength, and after curing what they did, they subjected it to the electrolytic corrosion test by submerging in a water containing 5% NaCl. It is basically kind of marine water or another synthetic chemical which they use, and they use also the electric current density, that is a 50 milliampere per meter square. So, it is very small current density they have used, and then they try to figure out whether there is already corrosion media density and maybe there are some cracks, then it will be kind of a electrochemical reaction will start, and finally it will reach to the rebar, and rebar already I mentioned is a steel reinforced bars, will reach to that, and then they use the two sensors on the surface. Now, another point came that this kind of concrete block they use the 5-side epoxy, so that there is no conductivity, there is no ingress of the water. So, they can really figure out what is really happening. So, only the bottom which was which did not have epoxy at all. So, the water can ingress from a bottom only. So, that has been shown over here. The two sensor position on the contact media on the specimen, particularly where media was contact and then the coated with epoxy. So, top it cannot ingress, and then receiver in this case finds a particularly reflected waves from a specimen, or maybe from bottom or maybe sides, but water ingress can happen only from a bottom, not from other 5 sides. And then they showed the results after 90 days of the exposure to the electrolytic corrosion test. They find some sort of the surface, and you are able to see the deep crack, and that has been noticed after 98, roughly 3 months plus. And then one day on day 98th crack has spread to the width of 1.4 mm. So, it is visible as such. So, in this case on the surface itself is visible. We really don't have to we don't really require ultrasonic testing in this case. However, but if you want to simulate, and then on the 19th day if we predict and we write an algorithm and we really see on the 98th date this kind of crack can develop, that will be very important. So, initiation of the crack, subsurface, and then finally it is reaching to after 90 days and 98 days on the surface, and we are able to predict well in advance. That is what then the overall good results as such. And then what they have shown the before electrolytic test, they are able to show the black color, and then with the passage 90 days they are able to see that minimum energy of the green color line only. So, the amplitude is minimum in the green color. So, this is what they were trying to predict. If we are able to see there is a continuous dye and the continuous reduction in energy level, with the time, then there is some crack, and then the damage will be continue. And if we are able to write algorithm on that, we can predict the life or residual life of the concrete, healthy life of the concrete. So, what can be said, again the same reference which has been picked up earlier, we say that after 24 days of the corrosion test, amplitude of waveform is lowered or maybe it is reduced. This finding holds true for the 94 days to 90 days. 24 days we find a lesser amplitude in many places. Of course, some places we are able to see the higher amplitude, but it is basically we need to look at the major portions. So, statistically at 1 or 2 places there is a possibility the fluctuation happens by whatever reason, because sensors being subjected to the different kind of the environment, sometimes vibration or maybe this when we are checking, while green is clear, and then that is what has been mentioned, that this finding is same is holding the true for the 24 days to the 90 days, indicating the reflection is scattering due to the corrosion induced cracking is occurring over the time. That more and more crack, more and more scattering of the waves will happen, and the reflection energy or energy which we are collecting back will reduce. So, Ultronic what they have done, they have used the P waves. In lecture earlier lecture I mentioned what is the P wave. They kept a velocity roughly we say that 4022 meter per second, and then refraction what they estimated initially, what will be the when the reflection should come back, it was roughly estimated 20 microsecond, however they found around 75 microsecond. So, there is that indicates very clearly there are cracks and there is some sort of scattering, and that is why even the return of complete energy is not within a 20 microsecond, it takes much longer time, is almost 75 microsecond. And then we know very well that this kind of tests are continuously done for the microsecond a second, and we need to really observe how fast it is really reaching to the surface. Now, today in this lecture we are going to cover one more what do we say that technique, that is what we call is a radiography NDT or radiographic test, and why we are using and how, what are the really main aims. We say that is in this radiography uses X-rays if there are thinner section or maybe the density of the material is not very high. So, they use X-rays. However, they can use the gamma rays if the sections are thicker or there is a high density. Of course, gamma rays are very rare because it is a very energy intensive, and then it has a number of repercussion, health hazard issues. So, we do not go with the gamma ray immediately, but that also comes under the radiography NDT. That is why we are covering this lecture. So, it uses X-ray or gamma rays to penetrate object or material to examine the internal structure. So, we do not go with a surface examination, internal structure, and then we want to really reproduce what happens inside the body or inside the body of the structure. Now, it requires sources for X-ray or gamma rays to emit the radiation towards object being examined. So, there need to be a kind of and then the source of these rays, and then there should be direction at point, whichever point we want to really impinge or send, and then examine the surface or maybe examine the object in complete volume, not only surface. Then this what will be output as such, it produces images which will be known as a radiograph on a film or digital detector. So, in a film is basically classical radiography, and then on a digital detector is something like a new digital radiography. Based on that, we classify in two categories. We say the classical radiography, and we say it is a digital radiography to disclose any defect or anomalies within the surface or within the material as such. Now, what are the good points? It can be used for ferrous and non-ferrous material, because there are few techniques which are useful only for the ferrous material, and we will try to show that maybe magnetic particles, they are only useful for the ferrous material, while this kind of testing can be done for both ferrous and non-ferrous material. It can be used for the thin and thick structure, as I mentioned that thin structure X-rays are good, thick structure gamma rays are good. And then another point comes like they capture the images either on the film or a digital form, and it can be stored and then even can give a good guidance in the future for the comparison purpose. So, it can be very useful for the trend analysis as such. Of course, what are the major issue? Major issue is that they have stringent safety protocols and regulations, and then the reason being the person can get affected with this kind of the environment, even the environment itself can get damaged with this kind of radiations. So, that is the earlier I mentioned that we have two categories, digital radiography, conventional radiography, and then what we say that we prefer to go for the digital radiography, because conventional is now age old technique. We should focus only on digital radiography. It increases the productivity, it enhances the sensitivity, it increases the environmental, basically it causes a lesser damage to the environment, reason being the lesser radiations are required. And then now in these days with machine learning, we also know that image processing tools are also continuously enhanced. So, we can use image processing tools with that, and based on that we can say that it is causes a lesser losses, lesser resources. So, it is a cost effective or cost saving. So, digital radiography will be preferable compared to the conventional radiography. Again, if there are failures on the surface, we should not come to the radiography at all. We can examine from other sources. However, we want to look at the internal details, and well in advance we need to figure out what is the really sensitivity of various cracks, or if there is a possibility of corrosion which is getting increased. Particularly the one of the previous example, we examined something like the concrete which has the iron material and which can also corroded, and there will be some failures in that. So, for that purpose radiography will be a good option, or maybe can compete with other techniques. If we are able to find faults with other technique, we should not come to the radiography, but if we are not and we want much more reliable readings, much more reliable prediction, then we should come to the radiography. So, now I am just trying to go with some sort of case study. In this case, this has been covered in 2010, one of the reference paper, and then what they wanted to really use a radiography particularly for pipe. We know the pipe has internal cracks, some sort of failures, or maybe the surface damage, and we need to detect. So, that is why they wanted to go ahead with the radiography. The test sample they got from pipes, and then they use this technique for the two different thickness, 12.7 mm, 24.5 mm is something half inch, and 1 inch. And then the material of the has been already defined. The base material has been shown in this kind of table 2. So, it is like a low carbon, the percentage has been utilized in this case, and this is a grade is something like a API the material, and then it is a 5L X70, and it has been, the whole thing has been described in this reference. Now, they made a total 6 samples. That is why we are showing that there are total 6 samples, and then they wanted to really do testing for the welding. There are big pipes, when they get welded on the surface, what kind of the process will happen. So, that is why they made the 6 samples, and they wanted to simulate the condition of the welded junctions to investigate. And of course, they use a sample 250 mm by 250 mm, and that sample has been shown over here 250 by 250 in this, and there is a center portion has been shown, the welded portion as such, you are able to see over here. And then after obtaining the samples, they created some cracks on the surface, intentional cracks on the surface, so that we can do a testing comparison. Is something like a pipe is a steel pipe. So, in this situation they wanted to go ahead with a magnetic particle, they want to go with a conventional radiography, they want to go ahead with digital radiography. So, the overall comparison can be made. So, this is what in this case, the first case the examined is the magnetic particle investigation. We are able to see the surface crack on this portion. Right. So, this is what been shown in this case of the first case. Now, when coming to the conventional radiography, they found also that the cracks are visible with the conventional radiography, and then they found this technique also can be utilized. So, I find more cracks in magnetical particle side compared to this. Now, you are able to see here some sort of cracks over here, right. But if we go ahead, with the digital radiography, we are able to see many cracks with many branches, right. Now, the magnetic particle is basically for ferrous material. As we say, the radiography is for ferrous and non-ferrous material. So, even if I use for polymers or use for some other material, this kind of the process can be utilized. Now, we are comparing conventional versus digital, and we are able to see that many cracks. You can see here the cracks here. There are many branches of the cracks, many the portions of the cracks are visible. So, we say with a rectangular marked on the digital image, a collection of the fractures or maybe cracks with multiple branches can be seen. This image clearly depicts that these branch fractures, demonstrating that digital technique is superior and it has the ability to detect and visualize discontinuity. So, digital radiography method is more sensitive than conventional radiography method, right. So, we just say that radiography is better compared to the conventional radiography. Of course, if it is a magnetic material, a ferrous material, and if there are surface crack, I will not go with the radiography. But if it is a very minor cracks which are invisible, and then we want to go with the radiography, or there are pipes and inside surface are the cracks, then we should go ahead with the radiography kind of thing. So, in my words, I will say that in conventional radiography, image is captured using X-rays to exposed film, which is then developed and processed with the chemicals to produce the final images. See, something like what we take a photograph. Earlier we used to have something like images printed on a paper as such, right. So, those were final. Now, in these days the environment is changed, everything is digital. We capture the image which we like, we retain it, otherwise we delete it. So, same kind of process is happening with the radiography. Earlier there was a classical or the conventional radiography, we used to find out the final images. Of course, the final image which comes out, it depends on the quality maybe the skill of the person who is taking this kind of images. So, image quality was depending on a more like exposure setting and kind of the film processing, and then basically skill of the person who was operating here on those cameras. So, I can say the conventional radiography requires a manual manipulation of the exposure. Everybody has a different skill to capture the images. So, really the basically manipulation of exposure and chemical processing, in my view, those are not straightforward, everybody cannot learn. It requires a lot of practice, okay, and then require a lot of adjustments, initial exposure, processing films. So, it becomes like the individual effort of the person who is very good, only he can do or she can do. While coming to the digital radiography, it can capture the camera using the digital X-ray detector, and this can transfer to the electrical or the electronic signal. Subsequently the signal will be processed and the displays on computer screen. This process can produce a very high quality images, and it provides instantaneous feedback. See, earlier cameras and all, we used to get the image after 2 days, 3 days something. So, there was no immediate exposure or any immediate feedback. Coming to the digital radiography, we have immediate feedback available. If something has gone wrong, we can do more number of iteration immediately, and we get in a lesser time we get a faster and better results. So, digital adjustment also can be done, and now we have a variety of softwares which can be readily all the digital images can be manipulated and enhanced. So, those are important, we can say. Digital radiography overall is causing a lesser radiation doses compared to the conventional radiography. So, it is good from environment point of view also, and overall it gives a benefit in terms of the workflow, efficiency, image manipulation or capturing immediate image availability, and then the overall good results and then good feedback given how to go for the better and better results. Even the few iteration person learns and then can improve the solution. Now, I'll just cover the similar thing, corrosion testing, particularly for the steel reinforcement, and using this kind of radiography, we can say already I mentioned the reinforcement and then is important. So, again I am trying to repeat, we say corrosion can occur in construction industry when steel reinforcement is exposed to the moisture and oxygen, which happens mostly. Now, presence of crack will accelerate the corrosion process significantly. Now, from where the cracks will come, we say there are numerous factors. We know that there will be some sort of shrinkage after curing, there will be some sort of change in dimensions. So, those kind of shrinkage, even there are, we know the thermal expansion joints are also there. So, thermal expansion and contraction will occur, and then there will be different kind of loading, sometimes more loading, sometimes lesser loading, and maybe kind of cyclic loading as such. And there is a possibility of the environmental factor, which we have already covered in earlier lecture. These all factor will give a formation or will form the cracks. Now, once the cracks are formed, the cracks will enable corrosion agent to reach steel reinforced element by penetrating deeper into the concrete and making direct contact with the steel surface. Once the corrosion agent reaches to the reinforced steel, they initiate and foster the corrosion process. So, this is the well within the surface well inside, but concrete has a number of possibilities of cracks, and we even the naked eyes we have seen on the surface of concrete that there are cracks, while we are talking about the very inside cracks, and it reaches to the directly to the reinforced steel. And then once it reaches, naturally after that the electric electrochemical process is started, and then it will increase the corrosion rate. That is why in the earlier test we say that we want to know how the corrosion rate increases. So, in this case it can be shown that way. Now, corrosion causes the formation of corrosion on a steel surface which has a greater volume than steel itself. So, this is what I was mentioning, the corrosion, because of corrosion there will be more and more deposition on the surface itself. If there is a wear process available, then the material will be removed, but there is no wear process available, then only accumulation will happen, and more the volume will increase. So, in this case particularly rusting, so we say expansion of rust within a concrete generate internal pressure which exerts a tensile forces on a surrounding concrete, and we know very well that concrete is not very good in tensile force, and that is why we go hard with the reinforcement. But if reinforce the steel itself creates a tensile stress and loads the concrete, naturally that is a disaster. So, this is that we say this in turn leads to the further concrete fracture and the deterioration. So, once the crack reaches, allows to increase material or electrochemical and then the liquid or maybe solution reach to the surface, then everything will turn out to be like accelerated wear and accelerated corrosion and fracture. And that is why we say the combined effect of the corrosion and fracture. Here we are saying there is no wear, but still the corrosion and fracture can will combinedly work, and then it will cause the and it will cause the or maybe the hamper the structural integrity, and then finally it will durability of the reinforced concrete will be significantly compromised. Now, it will weaken also the bonds between a steel surface or steel reinforced and encircling or the concrete which is enclosing this reinforcement. There will be debonding between the surfaces. It will reduce the load bearing capacity of the concrete and increase the likelihood of a structural failure over the time. So, it is not instantaneous, but over the time failure will occur, and that is why we are going to cover one case study which will highlight those points. So, this is what we say corrosion testing, the radiographic the testing which has been done here. This is what we have showed earlier on the surface. Now, we are showing and using the radiography that there is a maybe possibility of subsurface, and then what we are saying in this case UN is basically an cracked sample. LC is that we have a something like a longitudinal crack, and LC if we try to bridge the crack, as I mentioned, if we use some sort of bridging media, something like epoxy inside the concrete itself, and then there is a crack and epoxy is getting engraced to that surface, it will cause a binding again. So, it will bridge. So, there are two methods, one is automated. If we do automation process, we keep some sort of capsule, or there is a manual bridging of the gap. on the, maybe we have seen some crack and we are trying to close it. Now, this is a longitudinal crack and this is the orthogonal crack OC, and then again the bridging of the crack using the manual process or using the automated process, and that is why the manually healed or automated healed word has been utilized for this purpose. Now, in all the cases when the starting position has been given, after 2 hours, after 30 hours exposure has been given. Now, what we are able to observe that this is a chloride ingress happens in each case, and we are able to see the more corrosion or lesser corrosion in this case also. So, orthogonal without manual it has been shown, in this case with automated healing also has been shown, and then the longitudinal we are able to see. So, everywhere we find that whenever this crack which has been healed with a manual process has been showing a better results in this case, while in case of orthogonal also substantially better result has been obtained in this case also. This paper has been published in 2018, and this says that X-ray radiography to visualize the rebar cementitious matrix interface and just the delay in corrosion through self repair by encapsulating polyurethane. That means they are using polyurethane to self heal the crack, and then they start giving a bonding to the crack and does not allow chemical or solution to ingress to the reinforced material. So, we can delay the corrosion based on that, and that is what has been shown in this case. And this is what I will show. Now, coming to the radiography completely, you can see here the white circle has been shown on the surface, and we say that this the testing corrosion impacts on the reinforced sample using over here we are trying to find out the radiography. Now, this white circle has been shown as a rebar. What is the reason? This all white circle you are able to see, these are the reinforced or rebars as such. And then what is the reason why we are getting white circles? We say that because high X-ray attenuation properties, this kind of material have a very high attenuation properties to against the X-rays. While in this case nearby this is still reinforced, you will be able to see the mortar. A mortar is something a mixture of the bigger particles compared to the sand and maybe lesser particles compared to the stones which we use for the concrete purpose. So, this mortar is kind of has been shown as a red color zone. You are able to see the red color and in this. However, in the red color also we are able to see there are some sort of yellow dots, and the yellow indicate there is a less dense region within the mortar, and then there is a possibility of air bubble, there is a possibility of crack, there is a possibility of corrosion. So, using the radiography we can really find out what is the really problem with the concrete which we are using. As I say, this white color circle you need to neglect, these are the steel bars. And then we need to look at what kind of the yellow color. If the more and more yellow color, naturally there is a more and more possibility of the failure. However, in this case you are able to see there are more and more yellow color as such in the surface. So, even though whatever we shown with the naked eyes, there is a contradiction in that, and that is why we say that we should believe as such on radiography results if we want long life. And then here in after 70 hours we are able to see more and more cracks in the surface that will lead to the failure. Now, and last one is in this case is the corrosion byproducts are shown by the gray areas, and these are the corrosion byproducts. If the corrosion byproducts increase, naturally the volume will increase and then more and more cracks will come. So, we using the radiography we look at only the yellow color, more and more possibility of void, more and more possibility of the cracks, and that will cause a more and more damage. And then either we remove the media or we remove the conductive path or we improve the property. This is what we learn from these kind of experiments. So, we say the experiments show healing longitudinal and orthogonal cracks, and it causes a delay on the onset of the corrosion. So, if I look at this LC, there is no healing as such. LC is a longitudinal crack and there is no healing, while in this case there is a manual healing has been done and there is a automated healing has been done, and we are able to see the lesser yellow portion in LC man or LC caps. And coming to the even orthogonal crack also we are able to see more yellow portion compared to here, while in this case manual we are able to see also the yellow portion, while compared to in automation we are not able to significant yellow portion in this case. So, this is what we interpret, that using radiography we can really look at what is really happening, and what indicates here the yellow portion is much lesser compared to the orthogonal and the crack or longitudinal crack. So, that means this kind of whatever the method they have used self-healing agents into the concrete, they are delaying the process, and we can really develop an algorithm on that, and then we can predict what will be the overall failure rates as such. With this I say thank you for attending this lecture.